Yeah, he does. All right. Our next session is on DA. I'm going to hand it over to the chair for that session, Shuguang Wang online, and Daryl Kleist here in the room. Daryl's going to kick us off.
All right. Welcome back, everyone. We're going to switch gears from social science to data assimilation, which is a very obvious going from point A to point B. So thanks for coming back. I'm going to be co-chairing the session along with Shuguang Wang, who's online. We have 6 talks, and we have plenty of time for discussion on the back end. So we'll probably hold off for most questions unless there's clarifying things that come up in the meantime. Shuguang, you are the first speaker, so I'm going to turn it over to you. Take it away.
Thank you, Daryl, for the introduction. My name is Shuguang Wang. I'm a professor from University of Oklahoma, and also going to serve as the director of this newly established multi-university consortium for advanced data assimilation research education. We have a nickname, CADRI. So on behalf of our team, I'm going to introduce CADRI to you all today, and thank you for the opportunity. Next slide, please. So CADRI is led by University of Oklahoma in close partnership with 5 other funded university partners, including Harvard, Penn State, Maryland, Colorado State, University of Utah, and 3 other unfunded university partners, UIUC, Albany, and City College of New York. Next, please. So CADRI will work closely with NOAA to achieve CADRI missions, including OER labs, National Weather Service centers, EPIC, and NOAA's corporate institutes and science centers. CADRI will also plan to collaborate with Joint Center for Satellite Data Assimilation, especially for education component. Internationally, we plan to collaborate with UK Met Office, University of Reading, and also the TDSA, standing for Transatlantic Data Science Academy. Next, please. So we all know what a data assimilation is and why it is important. But data assimilation's transdisciplinary nature is not often talked about. Data assimilation requires understanding of the mathematical algorithms, physical processes, and observations, modeling, high-performance computing, and data science. Next, please. So next-generation data assimilation is facing significant challenges due to the complexity, diversity of observations, and the future generation models, which is going to be run with very high resolution, resolving multiple scales, and coupled Earth system modeling. So because this is true, that means the next generation DA needs to be efficient, effective to integrate this large amount of data sets from both observation model and even a single Earth system component, like the atmosphere, for example. It's going to resolve a wide range of skills. We heard about, global model becoming conventional lying this morning. So that means the model can resolve a supercell and also the planetary scale. This requires the DA system to be able to provide analysis across multiple scales and quantify its uncertainty. Weather forecast will also rely on initialization across different Earth system components, especially at the interface. So this requires to advance coupled Earth system DA. And model error, we heard a lot about model biases and also the stochastic component of errors during the meeting. Without them being treated, no matter how advanced your filter is, ENCAF or non-Gaussian filter, you're going to correct in the wrong attractor. So we have to treat model errors. And with the diverse and complex observations, we'll need to develop new observation operator for remote sensing observations, fast, effective approach for pre-processing, quality control, and estimating observation errors. And of course, methods to treat nonlinearity and non-Gaussianity. Due to the transdisciplinary nature and its growing need, there is a serious gap in data assimilation workforce. This is identified by the U.S. Congressionally Mandated Power Report, and more recently, in the Phase 1 report from TDSA. I'd like to stress that to address all these challenges, we really need to sustain support for long-term innovative data assimilation research. And this is not going to be addressed over a 2 or 3 year period. This is also true for workforce development. So we really need long-term sustained support for data simulation workforce pipeline development. Next, please. So KAIJI is a comprehensive, collaborative, integrated research education R2O O2R program. It has 4 objectives. First, we want to increase the number of graduate student postdocs formally trained in data simulation with experience of NOAA UFS model and JEDI DA system. We want to enhance the global data simulation workforce pipeline. Through training and outreach, we want to perform fundamental research in DA to seek solutions to address challenging data simulation issues for UFS short range, medium range, and S2S predictions. We also want to promote R2O O2R. Next, please. So I'll touch briefly about research first and then our education component. So KAIJI proposed 12 research thrusts, and it covers a broad scope of the research topics, including novel data simulation algorithm development, leveraging AI machine learning in DA. And we want to improve forecasts for a wider range and nearly all UFS applications. We want to address issues in DA not just for one ERSYS component, but also couple ERSYS system. We want to advance the simulation of a variety of in situ remote sensing observations. KAIJI wants to promote R2O O2R by transitioning DA research development into operational forecasts. We want to implement new DA's capabilities into UFS NOAA forecast systems. Next, please. Okay, I'll go through the 12 research thrusts briefly. And the first 6 is about advancing data simulation for existing new observations. So you can see from the list, we want to advance the simulation of ground-based radar, all sky radiances to improve warm season convexity prediction, winter weather. We want to advance similar satellite data and identify observation gap for tropical cyclone genesis prediction. And we want to advance aerosol simulation to improve UFS, GFS aerosol forecasts, and advance ocean DA by a direct assimilation of Lagrangian direct data. I want to stress, given the breadth of UFS applications and limit funding, only a subset of the research thrusts are direct addressing hurricane DA challenges. However, the methodologies capability developed by other thrusts can also be eventually leveraged for addressing hurricane DA challenges. Next, please. The next 6 topics about addressing the advancement of DA methodology and capabilities. 3 of them are using machine learning AI in data simulation. For example, we plan to attribute model error and to improve S2S couple ocean atmosphere data simulation prediction by machine learning. Using machine learning to provide an estimation of the likelihood for non-Gaussian state-dependent observation error in the UFS CIS ocean DA. We want to explore the use of data-driven model to reduce the cost for multi-scale ensemble DA for RFS. We want to advance strongly coupled DA for S2S and also for short-range RFS forecasts for convection initiation, and also explore non-Gaussian satellite radiance observation error estimation implementation in GFS and RFS. Next, please. Okay, in addition to research, we also have a comprehensive education workforce development component. We want to use a new advising model. Students from KAIJI will be co-advised by KAIJI faculty and NOAA scientists. We want to advance our data simulation class curricula. We want to promote public awareness or acknowledgement efforts for data simulation through offering public data simulation training courses, public science workshop meeting. We want to promote global DA efforts through the exchange program with UK Met Office, University of Reading, and TDSA, and workforce pipeline development. We also want to enhance that through outreach program. Next, please. So briefly, we're going to invite NOAA scientists to serve either as a collaborator or co-mentor, or even more formally like committee members for the KAIJI students when they perform research. The level of engagement will be based on mutual agreement. We want to support KAIJI students to visit NOAA on site in person so they can learn NOAA working environment. Next, please. 5 of the 6 universities are currently offering grade level data simulation classes. We want to advance this curriculum with guest lectures and by including JEDI component. Next, please. And we also want to offer public training courses in DA through collaboration with EPIC UFS training every year, and also leverage AMS short course or NCAR colloquium, okay, on DA topics. Next, please. For the exchange program with UK scientists, we will invite them to serve as co-mentors of Kadri students, postdocs, and support our students to visit UK and vice versa. Next, please. Yeah, so alongside with the annual training, we also want to offer the science workshop and meetings in year 2, year 3 to promote community-wide DA research. And we also want, of course, leverage AMS, GHU, major conferences. In 2025 AMS meeting, there will be a Kadri session and also a panel discussion session on the topic AIDA. So we already invite NOAA as speakers in these sessions. Next, please. Yeah, for workforce pipeline development, focus on graduate study students and postdoc, but we also want to start engage with, for example, an undergraduate student in DA research and in DA courses. We want to have a GitHub code repository for collaboration, R2O, and co-sharing. And our website will house, our core, training materials, lectures, and so they will be freely available to students even outside Kadri. Next, please. So this is our planned outcomes. Number 1, we want to produce new knowledge and methods for data simulation. And we also want to increase the number of DA scientists that are ready to work for NOAA. And through potential R2O, we hope to help revolutionize forecasts from short range to S2S. Next, please. So in the next few slides, I'm going to share and briefly the status of Kadri's self-cycled JEDI DA system for UFS regional applications, RFS HAVS. It's a self-cycle system, which means you have an ENVAR component to produce the control analysis. You also have a self-cycled ENCAF, okay, for the regional model itself, which supplies error corrections to the ENVAR. So the system is flexible to run standalone VAR or ENCAF or the hybrid between the two. It houses various DA solvers from JEDI, and currently it's being tested for UFS regional models. And we just did our very first friendly user release to Kadri universities to start to help students to learn and test and eventually hope the system can promote their research efforts and R2O O2R. Next, please. I'm going to touch this very briefly. So this is about Kadri self-cycle JEDI regional MPAS DA toward RFS using radar DA as an example. One observation test shows the correction made by MPAS JEDI, FRE3LAM JEDI, FRE3LAM GSI show similar pattern. They all show reasonable cross-variable update for the wind as well. Next, please. So it's showing hourly cycling mimicking RFS for radar DA. And the JEDI MPAS analysis in the second row compared to the first row, which is background, is being correct toward observations, which is within expectation. Next, I'll talk a little more about HAVS, Kadri self-cycle JEDI DA system for HAVS, given this HFIP meeting. So basically, single observation test for GSI, JEDI, assimilating a single observation near the core shows very similar increments. That the meaning of that is to correct the location and also the warm core temperature. Next, please. This is a vert cross-section about single observation analysis increments. On the right, you show the increments from JEDI, GSI. They have differences, but also have similarities. We believe the differences about model level 60 is due to the difference of the two in vertical localization. Next, please. So I also mentioned in our self-cycle system, we have MPAS has own cycled LETKF, LGETKF as well. So the single observation test for LGETKF, LETKF also shows similar increments corrections as in VAR, similarly the same single temperature observation. Next, please. We also test the system using both environmental and vortex observations. And first, this is just an example for radio sound and job sounds. First, we spot the differences between the two in terms of observation fading to background. Next, please. Okay, this is increments for GSI and JEDI, assimilating the observations I shared in the earlier slide, environmental and vortex observations. So first, we see similar analysis increment pattern between the two. And we also observe differences. We believe the differences can be explained by their differences in observation quality control procedure, vertical coordinate definition, and the localization methods. GSI is using recursive filter. JEDI is currently tested with NICAS. Next. So there is this ensemble background forecast and free forecast component in the Kadri self-cycled JEDI system for HAPS. We also test this component as well. We can see the first row GSI's forecast versus JEDI forecast initialized by their own analysis from our Kadri self-cycled system for HAPS is producing similar subsequent forecasts. So all this saying the system seems to be working. And we also plan to continue collaborating with NOAA and other partners to further develop the system to support Kaiji missions. Next, please. This is my last slide about references. I think this is all for me. Thank you.
Thank you, Zhuguang. So we're right at time. You're co-chairing, so I'm assuming you can stay on for the session. Before we go to the next talk, I believe Aaron has an announcement.
Yeah, I just want to make a quick announcement on behalf of Molly Berenger, the Director of AOML. Current and former AOML employees and affiliates, if you could hang out for a couple minutes after this session has completed, she'd like to get a group photo. That includes those of you that are online. Thank you. Go ahead, Daryl.
Thanks, Aaron. Our next presenter is going to be Tom Alinier from Joint Center. Tom, are you online?
Yes, I am. Can you hear me okay?
You sound great. We're just pulling up the slides.
All right. Okay. Well, hi, everybody. My name is Tom Olinier. I'm the director of the Joint Center for Satellite Data Assimilation, the JCSDA, and I'll talk to you about a project that we're spearheading that's called the JEDI, the Joint Effort for Data Assimilation Integration. And just for everyone's awareness, the Joint Center is a partnership between NOAA, NASA, Air Force, Navy, and with associate partnership from UK Met Office and NSF NCAR. If you can go to the next slide, please. All right. So JEDI is the future data assimilation system for a variety of partners. And I want to stress here how much of a revolution it is in terms of converging towards next generation open source unified data assimilation across all the partners, but also private sector, internationally, academia, bridging between research and operations, and fundamentally building a consortium of jointness where we can leverage resources across agencies and teams and do more science and do less redundant technical work to achieve more science. So next slide, please. This is a notional timeline on the current transitional operations. So by no means it's intended to say, this is a date for transitional operation. It's more a timeline on the different applications and how there are actually code freezes and transition and acceptance processes for transitioning into operation, starting this month with the weather company, private sector, early in January, February with the Met Office, Navy in 25, and then US partners as well. Next slide, please. I think you're all familiar with that rainbow chart for the UFS, which is a great accomplishment for NOAA to have a lot more consolidation of a myriad of models in applications into a much more consolidated and coherent portfolio. However, this rainbow chart is only half of the picture. This is only for the model, and the model is only half of a prediction. The other half is data simulation. So if you can hit next, we have actually an even more potent message with that rainbow charts that we can draw for the data simulation. All these components are consolidating towards a unified data simulation system for the entire UFS portfolio, from space weather to marine to air quality and weather and hurricanes, of course. That is actually JEDI. So this is a major initiative that's really going to pay major dividends for NOAA. Next. So JEDI is a unified DA system with multiple configurations. How do we measure, how generic the code is? And so the right-hand side here, you have these different bars that are representative of applications. So these are actually a number of lines of code to assemble an executable for doing a cycling data simulation experiment with different models. So the global GFS and GEOS, or NOAA NASA global weather. Then the second one is with MPAS. Third one is for the marine DA with MON6, SAI6. And the last one is the NOAA MP for land DA. And all the blue and green stacks are actually different repositories that are shared and that are generic and shared across the applications. The reds are actually the model interfaces that are specific to each model, and they represent less than 3% of the JEDI stack. So that means that 97% of the code is generic and reusable across these different applications. So at the bottom, you have actually the names of the branding of these different applications, the GDAS and the HAFS and MPAS JEDI and SOCA and Glory and LandDA. All of them are pretty much, the same code that is interfaced with a specific model and configured in a specific way. But it's 97% the same code. Next. So really, the JEDI project has these generic algorithms. I'll go through a little bit more of what they are. Interfaces to 15 plus models, interfaces to about 60 observation types, from buoys to satellite radiances and so forth. Community software is about 1.6 million lines of code with 2,500 automated testing on a variety of platform, cloud, and on-prem HPC. We have a generic test bed that does the course quality control, and then it gets customized into these different applications. And here I'm listing the various UFS related applications at NOAA. Next. So another way of looking at it is we're the Joint Center building that fast train that we're collectively using to actually be more efficient and get to that train station that's about TRL, technical readiness level 7. However, the train station is not the end destination, so there's still customization and fine quality control and integration that happens in each individual application. So really, when I get asked a lot, when is JEDI ready for what I need? And the reality is, it's like asking Amtrak, when am I going to get home? I can tell you when you get to the train station, but then, the last mile basically is very customized and requires some I can give you here. Next. Okay, so let's dive into JEDI. What are the capabilities, how it is actually unique compared to any other data simulation. So all data simulation systems and algorithms are basically computing an analysis increment, a correction to your model background. You start from a model forecast and derive a correction that is a function of your misfit between the simulated observation and your actual observation you're getting from various instruments. It's a function of these different components, covariance matrices, the model, the forecast model, the observation operators. We're leveraging the object-oriented prediction system, OOPS infrastructure that was developed and is open source and developed by ECMWF that we've expanded quite a lot. So if you hit next. First, there's the whole suite of algorithms. Shu Guang mentioned some of them. There's actually a lot more, variational, ensemble independent data simulations, block long shows, control PERT, LETKF, LGETKF, particle flow filter, dual space, hybrids, and then we're developing also new techniques to have tangent linear adjoint models as well through these. So it's quite a long list, and we're continually expanding on this. Next. Then if you dive into the observation, so the algorithms just see these different abstract interfaces, and then they get instantiated underneath. So we have Yoda, that is our unified interface with multiple backends, but that basically separates completely the concerns. So scientists just get the observations without even needing to know what data formats or how they're distributed in memory, or what the metadata conventions are. This is all handled under the hood, and we have a data store that we call R2D2 that makes it really easy to access the data. Next. So observation operators, I mentioned we have a very long list of observation operators. They're now matching the capabilities of various operational centers, and we've also added a lot of new emerging instruments like commercial data buys and small sats and various conventional data as well. So it's a long list of data of observation operators for the atmosphere, marine, land, snow, and so forth. Next. The background error covariances is our SABRE, system agnostic background error representation, which is a suite of capabilities from diffusion operator, spectral operator, bump, which is a convolution. They are combinable, they're model agnostic, and we also have a variety of variable transforms that are able as well. So we can reproduce the GSI capabilities, and we can do a lot more with multi-scale decomposition too. It is something where you have, we see the benefit of having these generic capabilities. For example, diffusion was developed by a marine team and can be immediately tested for aerosols or other applications. So this is a great example. Next. Finally, I mentioned that we're interfaced with a variety of models. Here is a list. Some are toy models that we developed for our EDU version of JEDI for training. Some are very mature models. The bottom line is, because all these different Earth system components are interfaced with JEDI, we can really explore all the science and really exciting science about coupled data simulation. So that's actually something that is really one of the main benefits of the JEDI system, is that you can really start looking at Earth system data simulation in a couple ways. Next. So I talked a lot about the software. I mentioned that we have a few thousand automated testing in our continuous integration system. We're developing and supporting SpecStack in collaboration with EMC and Epic. And then that CI is basically leveraged through our joint testbed that we call Skylab, which is an end-to-end testbed that has data ingests, workflow, and diagnostics, so that we can actually run scientific experiments. This is just a nice example of our dashboard with variety of diagnostic we can look at for an instrument in experiments. Next. We've done about 8 releases so far with Skylab and Jedi software that is over 26 repositories. We support multiple platforms and including commercial cloud. The porting has been improved dramatically because it used to be an afterthought to port to a different HPC, and now it's more like made of a requirement to have portable software from the get-go. So it is paying off, and we've run multiple. Every time we do a release, we run these multiple experiments for weather, land, variable resolution. So we have actually a higher resolution area for global impasse grid that could be quite useful for, especially for hurricanes, aerosol weather, marine. So all of this is available on our website. Next. All right, so these are the final remarks. So this was a very high-level overview of JEDI as a generic system. You're going to hear a lot more from various presenters today about specific applications that are exercising this that unified DA system and fine-tuning it for specific applications. I think what I was trying to get to here is showing you how generic and flexible this system is and how you can connect and leverage the work that has been done elsewhere so that it accelerates your work. So this is a unique way of collaborating as developing core technology. If we're looking forward, really what's we're trying to do is make the best use of observations, accelerate their use, and squeeze out as much information as possible, looking at a coupled multi-scale Earth system, advancing algorithms, and especially integrating AI in our system and scaling on future HPC architectures. Our accelerating transition to operations between innovation and operations, and finally building community engagement and collective resilience on this development and in this project. Thank you very much for your attention, and I'll pass back to you, Daryl.
Thanks, Tom. You'll be able to stick around for the Q&A session, correct?
That is correct, yes.
Great. In that case, I'll go ahead and introduce myself, giving the next talk as soon as the slides are coming up. I'm just going to give a very quick highlight of things that are happening at EMC on the global DA system. In particular, some updates from the observing system in the past year, but also our progress on JEDI. Are you going to drive it, or do I have to hit something? We'll figure it out by the 4th day.
Yeah. Well, if people all use the same files, that'd be great.
Are you just going to drive it, or do I need to hit something?
We do have this. I don't. It's been.
I'll just ask you. That's fine. No need. All right. So I'll go ahead. Next slide right away, please. So just real quickly, I reported last year on some stuff we've been doing in preparation for the changing observing system. So while the agency priorities JEDI, we're all in on JEDI, we're focused on doing JEDI. We are not quite ready to implement it, and the observing system is not cooperating, so we have to keep getting new observations into the current system. So we do have some low-level GSI-based, operationally relevant development happening in the background, in particular to deal with new satellites being launched. So for example, in December of last year, we had to integrate NOAA 21, ATMS, and CRIS. I mean, polar orbiting microwave is the backbone of the observing system for global numerical weather prediction. These are the kinds of things we have to deal with. We have a new GOES satellite that's about to become operational. So we're going to have to get new AMVs and GOES radiances in the coming year. Hopefully we'll get that in spring. There is an entire commercial program in Nesdis who are purchasing rolling delivery orders of RO data on a roughly 6-month cadence that we have to adjust to all the time now. So I give this a bit as a warning as we start to go to privatization of the observing system and we start purchasing microwave smallsat, for example, and are expected to use the government purchase data as quickly as possible because these things are going to fall out of the sky. Our business model for integrating observations into the operational system is going to change. We have to change how we're doing business, and we have to do it quickly, or we're going to be buying stuff we don't know how to use. Another big thing that happened in this past year, I took over as DA chief in 2019, and I inherited this fun project to deal with TAC to buffer transition. TAC to buffer was mandated by WMO in the late 2000s. It was supposed to have been done by 2013. When I took this position in 2019, we were nowhere close to done. Many places are still disseminating both TAC and buffer messages for conventional data. I am happy to announce we are finally now processing both buffer and TAC data, and it's ending up in at least the global prep buffer stream. This has been a huge deal for us. It is an engineering nightmare. You are very likely going to find some interesting things in the current radiosondes in our prep buffer files, but at least I can say we are extracting as much as we can from the buffer disseminated data. This is a big deal. I'm happy we got this over the finish line. There's still some more, but we're working through it. Why this is relevant to this community, it means there's more data available. I'll show some examples in a little bit, not just from radiosondes, but I think it gives us a chance to use dropson data better. If we can get buffer messages and more information from the drops, I think we have access to more information we can tailor for use in the NWP systems. So this engineering nightmare has turned into a huge scientific opportunity. Next slide, please. So this is just one example of what this looks like in practice. We've been monitoring these TAC and buffer dissemination things for a long time. The panels on the upper right are just showing basically counts and fits to obs, either bias or RMSE, of what's in the old prep buffer and the new prep buffer. And if you just get more data, you can make the O minus S better because we're sampling more of it. So just by the process of averaging, we're getting hugely improved fits to the data. We have more information going into the assimilation system, and we're making better use of the stuff being sent over teleconnections. I grabbed one example of, it's impossible to see in this figure, but there are both black triangles, which is what we receive in the TAC messages, and then the red profile is what we construct by rederiving. We still have some limitations of prep buffer to 250 elements per profile. I don't want to get into that. We're not going to fix that. But we can at least construct a better profile from the buffer disseminated messages now. So we have a lot more information in the vertical by using this information, and this is now in the operational prep buffer stream. Next slide, please. So there's a couple of other things in the works. So in addition to dealing with, now that we got these observations in, we probably need to relook at quality control and air specification since we have more information. We've done a lot of work in trying to prepare for the assimilation of sail drone data. So sail drones, we have operational pathways now. NOAA is getting some data. We already assimilate the SST data, but we do not assimilate the other components yet. We had a transition project that was funded. We're nearly over the finish line. We're going to try to include it in an upgrade early next year. We've also been partnering with Woodbourne on some work, and we're going to try to get the Woodbourne observations. We're going to try to get the Woodbourne observations that are now being in our operational data streams into the prediction systems quite soon. We might have to do a little bit of re-engineering of some stuff on the front end, but that's a work in progress. We're preparing for GOES 19, of course. We're going to have to get the AMVs in there because the old GOES observations are going to go away. EUMETSAT is launching a bunch of new satellites we're starting to prepare for as well. And some technical information about some details in the minimization to try to squeeze every last bit of science we can out of the GSI without doing a huge investment in science. Next slide, please. So this has already been mentioned a few times, but we're planning for the next major upgrade to the global system version 17. The big change here is we're going to a fully coupled model. To implement a coupled model, we need coupled data assimilation. So we've been working very hard to prepare for the implementation of the coupled DA system. And in this case, leveraging JEDI for the non-atmospheric components. So the ocean system is going to be driven by JEDI. We're developing a land DA system for snow based on JEDI. We're implementing some novel science that's even our international peers are not doing, like exploring the use of strongly coupled assimilation for the land atmosphere problem. we're trying to do these sort of groundbreaking things within the context of version 17. Next slide, please. So just an overview, we're sticking with GSI for the version 17 upgrade. We're going to continue using hybrid for the Ensemble VAR with the LETKF to update the Ensemble perturbations. But we're going to add an early cycle update of the ENKF. So we have initial condition perturbations valid and ready for the GEFs. For those that don't know right now, the GEFs is initialized by 6-hour perturbations, not analysis perturbations, because the ENKF is only run as part of the late cycle. So we're trying to fix that so we have actual perturbations that are representative of the initial condition uncertainty that are not evolved 6 hours by a model. The marine system is going to be JEDI based, BOM6 and CI6, using hybrid 3D Ensemble VAR and the LETKF and JEDI. We have a new 2D VAR snow system based on JEDI. And we're working on this strongly coupled soil moisture and temperature system. This is GSI based. We're also going to work on porting this into JEDI. And I'm not going to talk about the new aerosol system today. Next slide, please. Vijay already showed this slide. This is initial results from coupled versus uncoupled cycling tests. This is 3D VAR only. It's sort of experimental resolution. Bottom line is that using coupling, we can make the median range scores better. That's good. And we have vastly improved SST. That's the panel on the right. So all of the early signs so far are good. We're rapidly progressing on the high resolution prototypes and then plugging in the DA cycling into these new prototypes to start full-scale testing in the next year. Next slide, please. You will not be able to read a single character on this slide. That's not important. This is here for reference. Just highlighting, we've been continuing to make some advancements on the use of all-sky microwave, in particular in the global system, that I think would be really valuable to start more accelerate some exploration of this in the HAFS context. I think the all-sky microwave progress we've made in the community is an untapped opportunity for the hurricane community. In particular, since GFS V17 is going to move to a new microphysics scheme, we've had to do some work to be able to properly calculate scattering that's consistent with the distributions that come from Thomson instead of GFDL. So this is also something that's going to be available to the HFIP community moving forward. On next slide, I just have one example. Just comparison, this is just cloud fraction for simulated radiances from AMSO NOAA 18 channel 2, GFDL based on the top and Thomson on the bottom. We plug this into cycling DA system in terms of large scale fits, the bottom right. We don't really move the needle, but when you start looking at the details and how we're using the observations, we have vastly improved moisture and vastly improved hydrometeors. This is a big deal for us, making better use of crowd impacted radiances in the system that's consistent with the physics that are producing the backgrounds. Next slide, please. So pivoting to JEDI, Tom already gave an overview of all things JEDI, so I'm just going to give you a quick update on where we are. We're sort of doing things in a multi-tier sort of way, focusing on accelerating the use of observation processing tools. So we have a lot of legacy decoding and observation processing software that we really need to bring to the current century. JEDI is the opportunity to do that, and we made significant progress there. We're obviously pivoting from GSI to JEDI, everything from the forward operators to the validation of the solvers to completely replacing the whole thing, hopefully within a couple of years. And then also accelerating our use and transition from GSI to JEDI for the other applications. So RFS, I gave my sales pitch last year that I need this community to get all in on JEDI. We've actually made really good progress in the past year that Jing's going to talk about in the next talk. Next slide, please. So just breaking this down in terms of the evaluation and prototyping, the green boxes were basically done. I can say with a straight face, we've completed these things. The red ones are the works in progress. So we're now going from having completed the UFO acceptance, so making sure the observation operators and quality control, everything's there that we need, to starting to do prototype cycling and plumbing tests. So we have versions of the model we can cycle with JEDI, with most observations, and the model doesn't blow up. So that's a good start, but we still have a long ways to go. We're hoping to have scientifically credible operational resolution configurations within the next year, so that we have something I'm calling implementable in FY26. Next slide, please. So I mentioned the end-to-end testing in particular because a lot of UFO acceptance work you may have seen in the past, what's happening under the hood is it's using GSI as a crutch to do some pre-processing. We've worked very hard to be able to build JEDI-based end-to-end testing to go directly from the dump files we produce in operation, so the buffer files, to pipe them directly through IOTA to connect to the model to compute the departures. So we don't have to use GSI to do some pre-massaging and data formatting to then plug into JEDI. So this is a comparison of O-Fs, looking at the raw output. So using the buffer data stream, this is for ABI observations. I don't know if the date's on here. The details aren't particularly important, but now we can, from the front end, the raw observations, compute O-Fs in JEDI, compare it to GSI, and they're qualitatively comparable. There's still some details we have to sort out in terms of quality control and error specification, but we're basically there. One nice thing that we've developed in-house, so we don't have to implement a bunch of converters on the front end to convert buffer into something else to then plug into JEDI. We've built a back end into the IOTA API, so you can read buffer files directly without ever knowing what's happening under the hood. It's basically a wrapper around some stuff we already have. This is important for us because I don't have to re-engineer the entire decoding and observation processing front end to implement JEDI now. I can directly read the buffer files into IOTA, deal with this in memory, and then carry on. So this is something we've developed and contributed to the repository. It's going to be available to the community more broadly. Next slide, please. So I'm under tremendous pressure to implement JEDI as quickly as possible. It's the agency priority. Here's our timeline for implementing into the global. So I mentioned we're aiming to have basically cycled parallel testing with credible science and something I can implement by Q3 FY26. So less than 2 years from now, I need to have the science and the capabilities ready for something we can begin the transition to operations. This is being tracked very closely. We have a formal project plan. We've got an infusion of some new resources. We have a huge team working on this. We have the right people in place. We've made a lot of progress in the past year, and I'm confident that we can pull this off. The next step is figuring out how to leverage all of the developments we have going on now to make sure they're extendable where appropriate to the other applications. Right? We don't want to be doing RFS JEDI in parallel to HAFS JEDI in parallel to whatever other application we can imagine in parallel. Because as Tom mentioned, so much of the code is generic and reusable. So making sure that we stay connected across the development pipeline. So we're doing this in efficient manner. We're not going to get a blank check to do all this stuff. So we have to be efficient. And I think we have opportunities to do it now that we are making significant progress on the global side. Next slide, please. So in summary, we're working very hard towards V17 of the GFS. It's going to be a coupled system with coupled DA with the added wrinkle that we're going to implement in early cycle ENKF. And we're making huge progress on JEDI. And we're looking forward to getting this over the finish line. And that's all I have. Thank you very much. So we're going to continue talking about JEDI, and Jing's going to talk about the progress at EMC on HAFS JEDI.
Good afternoon, everyone. So my name is Jing Cheng. I'm following what Daryl just introduced about JEDI transition in the EMC for the global. I will introduce on behalf of the EMC HAFS DA team to introduce the current progress for the HAFS JEDI related transitions. So first of all, I would like to acknowledge all the co-authors. So this is definitely a teamwork. Without them, we cannot keep everything on track. So a little bit introduction, as a lot of previous talk already mentioned, JEDI is the next generation data assimilation system, and HAFS version 3 is planned to use the JEDI as the data assimilation system on the version 3. So by then, when everything is ready, well-tuned, it is expected that the JEDI-based HAFS data assimilation will meet or exceed current GSI-based HAFS DA capabilities and the performance characteristics. Please. Thank you. So this is what our current HAFS DA system look like, which is based on GSI. So so far we can do using GSI, we can do 3D VAR, 3D ensemble VAR, 4D ensemble VAR, ENKF, and VAR ENKF hybrid method. And we can work with GLAS ensemble members, HAFS ensemble members, and also a combination of both. And we can do data assimilation on either an inner domain or the parent domain, or we can also do the self-cycled DA for the net using the dual resolution approach. And for now, currently, there's no ocean DA in our current HAF system. So moving forward to JEDI. JEDI is based on a modular platform, which can be very flexible to work with multiple models and observations. So you can tell it has multiple components. Each component has its own purpose or functionalities. And here for the HAFs, we kind of pick all the components that we need and put everything inside a repository, which named HAFs app, HDAS app. This is where we host all the HAFs JEDI related components. And this is also the place we kind of use it to record our current development progress. And also there's a directory inside the repository named the HAF test, which we store our benchmark case and the validated YAML files. So in the future, if anyone is interested or want to start working on HAF JEDI, this will be a good starting point. So in the next several slides, I will follow the general procedure of DA to introduce how we use JEDI platform to facilitate data assimilation within HAFs. So I will first go with the background and then the observations and then the JEDI DA method. So first of all, the background error occurrence estimation. For those who are not familiar with DA, this is how we estimate the model error distributed spatially. And also by using this info, we can determine how observation data should be weighted relative to the model background in analysis. So in the JSI currently, the HAFs DA is using hybrid ensemble var method, which is a combination of static B and ensemble-based B. So, but in our HAF JEDI development stage, right now we are using the pure ensemble var, which is using background coherence estimate by the ensemble, estimated by the JEDI's ensemble members. Why we're doing this? Because for now, based on other EMC DA groups' experience, the Sabre bump is not ideal for the operational use. So currently, there's a new Sabre function called MGBF. It's under development. So in the future, we decide to use, also going to move to MGBF to use that to estimate background coherence and also apply the localization and the balance strength constraint using through that method. That's why. So right now, so far, we just stay with the pure ensemble var method. Yes. Okay. So and then, as I mentioned before, so still we need for now, if we want to do more tests, we still need to rely on the bump NICAS to do localization. But in the future, we're going to move away. So we didn't jump deep into the bump NICAS. We just do some simple tests to determine the horizontal and vertical localization scales, and use that to do our following test. Okay, so this is just an example how we decide the vertical localization scales, and we compare the increment with the JSI for single observations or multiple data observations. We compare that the increment on the vertical levels with JSI and pick the most similar result. So there will be slightly difference because the JSI for localization they're using log P coordinates and the JEDI was using sigma. So there will be slightly different, but we just pick the most similar one and keep going. Next, please. And then for the observation part, so we rely on the IODA to do decode or encode the observation data, and also IODA can provide spatial and temporal matchings, and also some observation-based diagnostics. And then we need to establish the forward observation operator for each observation type in the JEDI UFO, and adding the QC process and also adjust the observation error based on that. After we finish this part, we need to validate the HOVX, validate this process against the JSI. So currently in the HAF JSI, we have in the gray box, at least all the observations currently assimilated in the HAF JSI. And the types of observation that I list here in bold is what we starting working on, already test on the types in the HAPS JEDI. Okay, here is an example how we validate the H of X against the JSI. So we always start from a single observation test, and then we move to the, if it looks good, we will move to the multiple observations. On the right-hand side, this is an example from all the sounding data for all types of observations, including wind, specific humidity, and also temperature and station pressures. Could we move forward? And during the validation, we realized it is not possible to get 100% match when we validate against the JSI. Why? Because there are many differences underlying. So, for example, the analysis grade is different in the JSI and in JEDI. JSI was using the rotated B grade for HAPS DA, and the JEDI is using the model native grade, which is a cube sphere grade in this case. And also there are some difference in the CRTM schemes and some difference in the underlying the control variables during the data assimilation process. So here I just list an example of how the difference in the analysis gradient can cause the difference in the H of X validation. This is the courtesy of Dan Wu, who is working on the HDOB data, and she found there's a large H of X difference in close to the flat level, which in this case is like, for example, in the level 37. So on the left-hand side, those 4 panels is actually the different level wind field distributions. And you will see there's a purple dot. That's the location the observation should be. And so to calculate the H of X, we need to interpolate the variable from model grid onto these observation locations. So when the horizontal gradient is like small, such kind of interpolation is fine. You will find the H of X calculated from JEDI and JSI are very similar to each other. However, once you move to the large horizontal gradient, such as on the level 37 here, a slightly difference of the model grid location will cause, actually once you apply the interpolation onto the model, onto the observation location, the H of X calculated H of X will be, have a very large difference here. And on the right-hand side, actually, we also did some tests to see how much this mismatch of the analysis grade can cause. So when we choose in JSI, when we set the grade ratio as 2, which is like a 6 kilometers in this case, and the difference is huge. It's like around 5.3 for the meter per second for the wind field. And once we switch that grade ratio into 1, which is more close to the cube sphere grade, and that difference reduced a lot. So that's all for the observations. And then we also, for HAPS, we also test the JEDI provided the method. Currently, those 4 methods I list here, we have passed our test, and they all look functionally. So next, please. So those major components are, we figure out the most those major components. We kind of integrate this JEDI analysis process into the HAPS workflow, and that's how we ingest a JEDI here. We add some process in the observation proc, and that's where we use the IODA to process the observations, and then we also add the BAP-NICAS to produce to generate the localization files that we need during the analysis. So then we actually made some preliminary tests using that workflow. So here we picked 2 hurricane cases on 3 cycles. Why we're using so many cycles is because due to our current limited type of observation that we can put into the system, it's hard to find a cycle that can contain all the observations, in 1 cycle. So some observations are in some cycles we only have two types of observations, and some types we have the other two types of observations. That's why. And we test this with the 3D ensemble var. And currently the data inputs we get here is GOES AMV data, AMS UA data, sounding data, and ATMS data. So before I jump into the test, the analysis result, I would like to mention that we found out there's the average DN running time for now is around 1 hour. This is for 40 JDAS ensemble members on 300 nodes job. And we do find there's, if we want to try to increase the nodes or increase the task, the memory and the running costs unexpectedly increased too. So that's something we actually need assistance from GCSD to solve this problem, because so far right now this like 1 hour time consuming for analysis is a little bit too long for operational use. So here is some preliminary result for Helena case. In this case, we managed to put into observation data from a satellite wind and sounding data. You can tell clearly once the wind field it's has some modifications for the wind field after we put into those observation data. And here is the increment for the temperature and the cycles. Here is the example for the Burrow case. Here in this cycles, we assimilate into the satellite wind data and the AMS UA data. And again, we can see clearly the increment in the wind field in the inner structure of the hurricane. And here is the temperature increment. And next, please. And this one is, in this cycle, we managed to add into the ATMS data, which is available here. And it also has some increment modification on the temperature field. So as a summary, so currently we plan to implement the JEDI in HAPS version 3. And currently we managed to put the necessary JEDI component and integrate it into the HAPS workflow and run a preliminary test with the limited types of observations. And I would like to jump into the issue, the future work. So first of all, still it's the memory issue that I mentioned in my previous slide when we run the workflow preliminary test. So that's something we really need help to solve. And then the future work part, once the MGBF is ready, we're gonna go back and then work on our background covariance part. And of course, we need to continue to add in more types of observations for the HAPS JEDI, and then tuning them with observation and model statistics. And then after that, we will move forward to the cyclings with or without HAPS ensembles. So that's all. Thank you.
Thank you, Jim. Was there a comment or something online? I heard a ding, but I didn't see what it was.
Yeah, I can read it out. Yeah, Connor Nelson asked Jing, I've been digging into the observations that HAPS has been assimilating into the version 2A. I asked some others this question recently, but in your green table of observations assimilated in HAPS GSI, it looks like AVI data is not currently assimilated. Is that correct? Question. If so, why?
Jing, we'll come back to that in the Q&A session. That's good. All right, so our next speaker is going to be from OU. Changhan, you online?
Yes.
All right, go ahead. Take it away. Yep.
Okay. Hi everyone. My name is Tonghan Li. I'm working in the multi-scale simulation and predictability laboratory led by Professor Shuguang Wang at the University of Oklahoma. Today I'll be talking our current research progress, which is related to using the novel observations to evaluate the background ensemble forecast at the ARIES interface from a self-cycle HAPS data simulation system for Hurricane Fiona 2022. This work will be submitted later in this year. Next, please. First, I would like to introduce the recent OU map on research operations efforts for the HAPS in cooperation with NOAA EMC, which include the simultaneously multi-scale data simulation with scale-dependent localization for the HAPS for DEM VAR. This has been implemented in 2024 operational HAPS. The second one is incremental analysis update, which is implemented in 2024 HAPS real-time demo, and is expected to be in the next operational HAPS. Next, please. Okay, so let's talk about today's topic. Just a brief slide to show the background and overall goal. As we know, oceans are virtual heat and energy source that play a critical role in the development of the hurricanes, working in conjunction with the atmospheric changes. Tropical cyclone intensification is highly influenced by the air-sea interactions, which can be complex when the TC interacts with oceanographic thermal distribution and profile. On the right, a cartoon shows the role of the barrier layer in the hurricane intensification. Next, please. However, current data simulation practice tends to treat the ocean and atmospheric components separately, causing the inconsistency at the air-sea interface. So if we treat the Earth as a unified system by using a strongly coupled DA, it can provide an avenue to obtain a consistent analysis for the coupled atmosphere-ocean system. But before doing so, one critical aspect of the strongly coupled data simulation is to establish a physically and dynamically consistent background error covariance across the air-sea boundaries. The overall goal of this project is to advance the background ensemble covariance at the air-sea interface toward the eventually UFS have fully coupled data simulation. Next, please. A field campaign was conducted during the Hurricane Fiona 2022, where unique observations sampling the properties at the air-sea interface were collected. These observations include the Saildrone, glider, SFMR, and the paired dropsum and AXPT. Saildrone measures air-sea interface variables, including the atmospheric parameter and oceanic parameters, such as wind, air temperature, water temperature, and salinity. Paired dropsum and XPT allows coherent measures of the atmosphere boundary layer and ocean thermal structure data to the depths of approximately 400 meters. Next, please. So in this talk, the specific objective is to evaluate the background ensemble at the air-sea interface from a self-cycles HAPS data simulation system, using the diverse and novel observations from the field campaign during Hurricane Fiona 2022. Next, please. A quick experiment design is shown here. We used a self-consistent, self-cycled HAPS dual resolution EMR atmospheric DA and coupled with ocean model during the background forecast for Fiona. The simulated observation and physical schemes are the same as those in HAPS operational model. Next, please. First of all, I'm going to demonstrate where and what kind of observation from the Fiona field campaign we use in this study to verify the 6 hours background and background ensemble at the air-sea interface. On the left, this shows a specific time for the location of Fiona center associated with some dropsum, XPT, and Saildrone as shown in this figure. And two Saildrone observation number 1040 and 1031 will be used. So on the right is the Saildrone location with the Fiona's track. You can see they are very close to the track, so we plan to use that as a verification method observation. Next, please. Here is the outline of the results in this talk. In a couple of following slides, we will show the 6 hours background control and the background ensemble verification. This verification process will cover 3 different key levels. The atmosphere boundary layers by dropsums, the upper ocean layer by XPT and gliders, and the air-sea interface by Saildrones. Next, please. The first verification is in the atmosphere boundary layer against the Saildrones. From here, we see the blue line is the 6 hours background control, and the red lines are the 6 hour background ensembles. The green line is observation from dropsums. The upper panel is a height-dependent profile at the radius of maximum wind for temperature, moisture, and radial wind. We see that the temperature has a negative bias above the surface, And then the moisture has a negative bias as well below the 3-kilometer height. Both observations for outside of the ensemble envelope. And on the right, the radial wind also has a negative bias within the 500 meters. And the bottom panel is the azimuthal mean verification of the boundary layer structure against the drop zones. These figures are temperature, moisture, and wind speed, along with the normalized radius of maximum wind. Here we see the model captures the variation well along the radius of maximum wind, and most observations are inside of the ensemble envelope, except for the temperature outside of radius of maximum wind. Next, please. The second one is a verification in the boundary layer and the upper ocean layer from the paired drop zone and XPT observation, which means they are at the same location. Again, blue line is the background control, red line is are the background ensemble, and green line is observations. This figure shows a height dependent profile in the atmosphere on the top and then ocean on the bottom, respectively. For the air temperature at the air-sea interface, like the box, the control run is very close to the observation. For the temperature in the ocean mixing layer, like until about 450-meter depths, the control is close to observation, but have some negative bias. For the temperature in the thermocline, observation for outside of the ensemble envelope, and the negative bias is greater than the mixing layer. Next, please. When it comes to the water temperature in the upper ocean layer against the gliders, here we have water temperature time series in different ocean depths. We can see that the model by the blue and red has a negative bias, and then the deeper layer has more negative bias. These two are consistent with the result we just shown in the last slide from the XPTs. And we also can see that the ensemble spread is too low to cover the observation, mostly. Next, please. Okay, from here, we will focus on the third part, which is the background ensemble verification at the air-sea interface. These figures are time series of air-sea interface variables from the sail drone. We see that the model can capture the variation pattern well, and then the model wind speed and sea air temperature performs better than the moisture. But you can see the observation for outside of the ensemble envelope due to the negative bias for early stage of SAT and then overall moisture. Most negative bias in the model's SST and then ensemble spread is too low to cover the observation, which are consistent with the results from gliders and AXPT. Next, please. In this slide, we quantitatively verify the background ensemble variance following approach of Wang and Bishop 2003. This figure, the x-axis is the background ensemble variance, and the y-axis indicates the innovation variance with wind speed, SAT, moisture, and SST. In general, the innovation variance and ensemble variance of wind speed, SAT, and moisture are positively correlated. However, all ensemble variance under-predicted on innovation variance, especially for relative small ensemble variance. For the SST, the background ensemble variance is too low and incorrectly correlated with innovation variance. Next, please. Using the air-sea interface variable from the sail drone, here we calculate the latent heat flux and sensible heat flux to verify the model performance as a time series. The green bar on the bottom is the time period when the sail drone is close to the Fiona center. We can see that the model basically still captured the variation well in both latent heat flux and sensible heat flux. And when the stone is close to the cell drum, all heat flux increase due to the higher wind speed near the TC center. And the model heat flux has positive bias compared to observation, but the latent heat flux has larger positive bias compared to the sensible heat due to the larger moisture bias we just shown before from the cell drum. Next, please. The last part is the cross correlation between the sea air temperature and the sea surface temperature at the air-sea interface. In contrast to, on the contrary, before the result from the previous slide for the 6-hour background, here we conducted 96 hours free forecast from the time before Fiona hit the cell drum. On the left, the black line is the sea air temperature, and then the cyan is the SST. We see that the SAT decreased prior to the SST decrease, and then also increased prior to the SST increase. So on the right, we calculated the time lag SST-SAT and its ensemble perturbation correlation. On the right, the x-axis is the time lag, and the y-axis is the correlation coefficient. We found that the SST has a time lag positive correlation with SAT and peaking at the 24 hours time lag, which is consistent with the observations from the cell drum. Also, the SST ensemble perturbation has a time lag positive correlation with SAT ensemble perturbation, peaking at the 24 time lag. So this may be because the ocean response to the hurricane is always later than the atmosphere component response. Next, please. Same figures, but here we calculate the cross correlation between the surface wind speed and SST. We added the ensemble performance as a red line here, and the blue line is the wind speed on the right, on the left. So you see that the peak of the wind speed is prior to the minima SST, which is similar but different sign to the cross correlation between the sea air temperature and sea surface temperature. On the right, again, we see the time lag correlation and its ensemble perturbation correlation. Both SST and SST ensemble perturbation have a time lag negative correlation with wind speed, peaking at like 30 to 36 time lag. This means that the model SST decreasing response from the surface wind has a 30 to 36 hours delay. Okay, next please. So in summary, we found that the background ensemble in general capture the variation pattern well at the air-sea interface, but with still with need some improvement. And the atmosphere boundary layer shows a negative bias and under dispersiveness background ensemble, especially for temperature and moisture. For the upper ocean layer, we found that the negative bias in the seawater temperature, especially for deeper layer, background ensemble is significantly under dispersive. For the air-sea interface, we noticed negative bias and under dispersive background ensemble, especially for SST and moisture, and positive bias for heat flux, especially for latent heat flux, and the background ensemble variance for SAT moisture and wind speed are positive correlated with the innovation variance, while the background ensemble variance of SST is too low and incorrectly correlated with innovation variance. And the last, the SST, SAT, and SST wind full field and ensemble perturbation have physically meaningful time correlations, showing the promise for the strong coupled data simulation. For the ongoing and future work, we will further advance the background ensemble sampling at the air-sea interface through the improved initial atmosphere and ocean condition perturbations and the model physics perturbation. And of course, improve the background ensemble for weakly coupled DA. And eventually, we would like to have strongly coupled data simulation in JEDI, which Professor Xu-Guang Wang just talked in the early time. Okay, thank you. That's all I have. Oh, sorry, let's back up. Yes.
Thank you, Paul. Stick around. We may have some questions for you when we get to the Q&A session. And with that, I'll introduce our final speaker. Hanseo Kim is going to talk about regional MOM6.
Okay, this is a very good segue. So I'm going to touch upon MUM6 and high resolution, which is 112 degree, quite different from the global MUM6 that you guys, AMC has done it. So it's quite different animals. Okay, next slide. Next. All right, so I'm here to report saying that we established Marine Jedi with the 3D IDA using explicit diffusion operator. We have, there are two operators available for Marine Jedi. One is Bumpernicus, and we find out the Bumpernicus it's less flexible and it gives more errors than the explicit diffusion. So we use and run it for analysis. We produce daily 3D analysis for 2022, but our interest is in the period of Hurricane Fiona and Ian in September, which the previous speaker has presented. And in this talk, I'm going to give you a flavor of the data impact study a little bit for the September in 2022. Next. And then I'm going to skip, actually, this one is a Marine Jedi MUM6 system, and the left one is Jedi, on the right side is the mother side, and then let's go next. And this slide shows that the observations for 24 hours for ingested in 12Z in September 17 in 2022 analysis. It's the top two one showing ADT left and then salinity on the right side. And the middle panel shows that the SSD, look at the coverage of SSD. Amazing for different sensors. And then one thing is in the con part of the large volume of SSD is that there is no SSD under the hurricane. So, but luckily, which is in this slide, it shows that the Hurricane Fiona is tracked there, that's the track. And the bottom two panels shows that temperature, in situ temperature left and then salinity on the right side, up 10 meters for that particular day. And then look at the open circles. We do have, luckily we have hurricane gliders operated by AOML, okay? So there are gliders, to observe, provide observations for hurricane, and that complements with the SSD. Okay, next. And then this one is start to comparing our analysis and two left panels showing that loop current frontal positions from Abysso in black, and then free run MUM6 in blue, and the 3D in green for pre-storm Hurricane Ian in September 24th. And then 7 days later, bottom one is the front changes. And then more like lines with the dots are the Ian's track. So definitely, 3D in green improves the frontal locations and also, deviations from the Abysso ADT values from black. So top right panel top shows that the measure of the deviation of this curve from the ADT, lower value is close to the observations. Obviously, larger value is away from the observations. The blue line shows that MUM6 free run over the entire 2022, and the 3D bar in a green. And look at that, 3D bar. Let's fix it. The front is quite fixed very well. And then definitely that shows that the quite improvement to the bar. And the bottom panel on the right side is the loop current north extent. And the y-axis in a degree and latitude. The same goes with blue for free run, 3D is DA, and then black is ADT estimates. And look at this. blue, and green, and the black pretty much follows, especially hurricane period in the summertime. They're pretty good. That is important because we, Oceanside, in a couple of simulation, we are exchanging, we are passing SST and also sea surface currents. If we don't get this summer front correctly, an atmospheric side, we have a more ocean heat content or less heat content. Okay, next. So this is the Gulf Stream front. Top panel shows that sort of snapshot of the SSH from free run on the left side and the 3D on the right side. And we have 3 curves in each plot. Black is abyssal observations, and the blue is free run. Green, obviously, is 3D. Right. So that is a pre-hurricane Fiona before encountering the Gulf Stream side. Okay. Again, that modified Hausdorff distance, which is deviation of the from the observation, reference point for 3D persistently, and for the entire 2022. It's very persistent, and only 20 kilometers differences. Whereas free run, it goes up. Okay, so that means either the Gulf Stream separation is further north, or it has a lot of meandering motions going on, with a higher MHD. Next. And this is another verification. AOML, we collect the transport of the Florida cable for last 30 plus years. And using that observations, we do validate. The observation is in blue. And the free run, observation is in red. Blue is free run, and then 3D in green. Okay. And before hurricane season or after hurricane season, it's hard to make a distinction. But in the hurricane season, we definitely overestimate the transport by the free run, by constraining observations. But downside is that 3D during the hurricane, August period, it's a little bit underestimated. That the bottom panel shows, table shows that all statistics for entire 2022, and then also a subset of the data for hurricane season comparisons. But if you look at all the stats metrics, definitely 3D is performing much better. By the way, and the green black curve on the top panel is the RTOPS estimates. Next. This is one snapshot of the SST comparison. Top panel is composed of the free run A, and the left side, middle one, Ostia, it's 120 degree. And the C is the differences between them. And then the right panel, right column shows that in a history PDF format of the differences. And the bottom panel shows that the same story, but it's over the 3D. Definitely shows that reduce a lot of blue cold bias from the free runs by having a 3D data constraint at the bottom and the third column shows much improvement. And then that histogram on the right side tells you pretty much stat. Okay. Next. And then this is a sort of line presentation of statistics for the SST comparison. Okay, so free run is a pale blue on each correlation, and A, standard deviation of B, RMS E in C, and then skewness on the D. And free run is again, pale blue. And then there are 2 types of the data simulation. One is just only, we ran the data simulation for September only, which is in orange. And then 2020 entire year analysis in blue, dark blue. So I'm going to get into later, but this slide, gives us three take-home messages. Okay, first one, if we do data simulation of a short period, you might get this different stat, which is in general bad. And if you continue doing analysis for the long time, you have a better product. And then 2 lines in each component are data denial experiments we've done. And the green represents no glide for September period, and the real red is no ADT. Okay, and it turned out that there are no differences in particular this September between no glider, no ADT, but when you look at the skewness, there are quite differences in the later of the month. Okay, so red in the skewness pretty much without the ADT, skewness tells us all the difference temperature is pretty much positive, but with the without the glider is more so. Okay, next. And then this was again, we do checking out the Gulf Stream front on the left side, and then loop current on right side with the data without the glider and without the ADT. So this particular Gulf Stream at this particular time, ADT is in black, and notice that without ADT, that red line is pretty much almost coincide with the free run in the blue. Okay, and with all the observations and the data analysis in green, it's pretty close without the gliders. So in other words, in this particular case, in situ observations make little impact on the frontal positions, which is shown at the bottom time series. Okay, so blue and red close enough, but green and then green and then what is that? Green and the magenta pink are absolutely close to each other. But the story, it really changes when you go to the loop current frontal positions. Okay, so free run, yeah, it's pretty much almost the distance, MHD distance is about the 9 kilometer up to September 17th, and it drops down to almost 30 kilometers in blue. And the data simulation analysis products in green shows a pretty, drop down that distance quite almost 7 days earlier, although it switches back on, but it kept, pretty low afterwards. But when without data ADT in red, well, it has a little bit, showing larger errors in the early part of the September, but it gets bigger in a later time. And when you look at gliders, pretty follows with the free run. Yeah. Next. And then this one is, we are looking at the comparison in situ simulations with or without the data. On the left side in the TS diagram, observation is in red and the model is in blue. And the middle panel and the bottom figures, second figure of the bottom panels is coming from the 3D analysis, and the far right is a TS diagram without the gliders. So definitely having a data constraint, we do have a better simulation of the subtropical underwater, which is pretty much residing in arm side of the TS diagram, which is around the 25, 20 degrees, and the high salinity, which is 36 PSU side. And Without glider, you may see a lot of underestimate of temperature. Underestimate temperature at the lower layers on the far right side. Yeah. Next. And skip. Okay, this one is the Ian case at the September 24. And then those all observations to verified in all the cross points in the top middle panel shows that. So we checked only individual TNS profile, and then 1 point just off the Mississippi River, we do pretty well simulated loss salinity part on the bottom left TS diagram. And the middle TS diagram, this one shows that the worst simulation we can have. That particular location is persistently underestimate the salinity, and the weed has a sort of weird kicking in the location. So we are thinking this one has to do with the background errors that you used, which derived from the quarter-day global MOM6. So we need to check the background errors. We need to update the background errors. And then far right side, I have 3 scatter diagrams. Again, model is blue and observation in red. Top panel is the 3D analysis, and then bottom 2, and then no gliders on the left, and the no ADT, and without any gliders, we compromise all the temperature and salinity at the lower depth. Okay, but with the ADT, somehow we can correct the temperature salinity and then the lower level. And without the gliders, in particular Gulf of Mexico, we are mainly losing Gulf Central water mass, which is about 20 degrees, and then 34 PSU side. Next. In the conclusion, this work is the first ever produced MOM6 analysis using Marim Jedi with the 3D DA. And we also demonstrate the improvement of forecast skills, correcting the northward Gulf Stream separation, predicting better loop currents, Gulf Stream fronts, and the water mass properties in the upper layers. And this loop current and the Gulf Stream, that's more like a larger scale, but TS improvements it's very important, especially in the initial conditions when you simulate hurricane side. And the impact, again, SSH, that impact on the larger circulation and the thermal currents, and the glider impacts on the local ocean conditions, especially vertical structures. So we need more subsurface observations for better initial conditions, especially hurricane simulations. Thank you.
Thanks, Zach. All right, so we've left about 20 minutes for Q&A and maybe some discussion. So first, any questions, either online or in the audience, for any of the presentations? Right.
We did have the question that Connor had asked. Okay, thanks.
So, Hyun-Suk, what was your background for the MOM6 runs? Was it the global MOM6?
I used the ICOS. So I used the ICOS nowcast. Yes, it's the same, resolution. It has a.
But it was the MOM6.
It wasn't a MOM6. No. No, if you guys have MOM6, it's a quarter degree.
We're working on it. Jing, can you see the question online now?
So to answer the question from Connor, no, I just confirmed with our team lead, we do not assimilate API data in HAPS version 2. And the reason is the OutSky API it's still a research progress. It's actually the OU Xu Guang's team is still working on it. It's not well tested in the HAPS, operational HAPS yet. That's why we are not using it so far.
All right, we have another question online. Can we say that we improved SST forecasts across the Atlantic Basin? And if so, how far out?
Yes, I think so. All my stats proves that improvements for forecast. So all the lines we've shown is based on the 24-hour forecast before next analysis takes place. So definitely we improved SST's forecast. And then how far out? Because I did only 1 year, so pretty much 1 year is pretty good. I'll say. By the way, it's a 24 hours analysis.
Thanks, Hansuk. Other questions? Maybe I'll throw one back to both Tom and Xuguang. Maybe from both the cadre and Joint Center perspective, can you say a little bit about the role of JEDI EDU, JEDI more generally, for both education, training, capacity building, and sort of, the next generation of people I need to hire?
Who is going to speak first?
Your co-chair, you should go ahead.
Oh,
You can
okay.
go ahead, Ina.
Yeah, in terms of JEDI, we definitely see this as a great opportunity to include this in classroom teaching and also public training, and to help students or those attending the training to understand the data center theory, and then also have some hands-on experience learning the theory. Yeah. And what is your second part of the question? Is it all about JEDI or there's another one?
And JEDI generally within, so we're committed to JEDI for future operational systems, but maybe saying more about the role of JEDI for training, capacity building, the next generation workforce.
Yeah, great question. And so we also plan to, in addition to JEDI, which is tied with the simple model, as Tom shared, we also want to include JEDI UFS model as part of classroom teaching and also in our training as well. I think this will be expanding upon the existing training capabilities, which traditionally focus on just methodology and also like simple model. But this gives the students and who are attending a training an opportunity to learn the real world application of data simulation and using JEDI and US model. Yeah, we definitely want to include both for education.
Yeah, let me expand a little bit on Xuguang's remarks. So the reason we started JEDI EDU at the Joint Center was initially we needed some easy ways to do practicals or JEDI academies, and also to have use JEDI as a tool for teaching for a summer colloquium. And quickly we realized there was a lot of potential to connect with universities and integrate JEDI as a teaching tool for integrating this in the curriculum for the DA teaching. Our goal is basically to build a sort of a continuous seamless ramp from toy models to very complicated operational grade models, and have as little seams as possible, so that gradually folks can evolve to very complicated operational grade systems and have all these tools ready.
Thanks. Any other questions or comments here in the room? Sir.
Carol, to you. So you have a buffer to iota for atmospheric side. Do you have ocean side as well?
Ish. It's a work in progress, but the infrastructure we built for both the converters and now the back end, we're working on extending that to non-atmospheric observations. The goal is so we can directly integrate the observations from our tanks and dumps into the same pipeline. So we're not there yet, but we're working on it now.
So there can be separate script. For example, I want to have data from ERDAP, different data portal. I have to use a different script for IO that then.
At some point, you have to tailor the converter or how you're using the interface to the specifics. But in general, there's now a toolkit of reusable software that can be applied more broadly to a broad suite of applications. I mean, we're using the same class of converters for everything from atmosphere to marine to aerosols to retrieval and all kinds of stuff. So this stuff is now ready to be deployed through everything. Yeah, Tom, go ahead.
Yeah, I just want to emphasize what YODA is designed to do. So YODA is the interface for observation data access. The whole idea is you have a standardized interface, and under the hood, you can have multiple formats. As a scientist, you shouldn't even need to know or worry about it. So the whole idea is, YODA is flexible and can handle multiple formats. Of course, if you're actually needing a new observation or an observation that doesn't have a YODA converter yet, then you'll have to develop it yourself. But basically, if you're leveraging some capabilities been developed already, then you can actually tap into the various YODA backends that have been developed. So it's quite flexible, and potentially YODA might change the format in the future. You wouldn't even notice. You wouldn't even know.
The goal is to make the stuff happening under the hood so the user doesn't have to care. Yeah. And from our perspective, I don't want to be converting all the incoming data into buffer until I retire. That would be nuts. So as we have NetCDF and other formats coming in directly in native format, we can tailor the converters to streamline the entire processing, have less data movement, less conversion, that kind of thing. Fenglin, go ahead.
On the same topic, so talk to buffer conversion, how far it goes back? Suppose we want to do a reforecast reanalysis back to 30 years ago, will be ready.
So right now, we have a joint project between EMC, PSL, and NASA to build an archive for reanalysis called NINJA. It's currently only atmospheric observations, but we're starting to add oceanic stuff. It's basically a homogenization of the input data records for CFSR reanalysis, MERA. We've done some cross-validation, and we've started to bring in reprocessed observations. What you can do is use the back-end IOTA converter we've already built and basically use any observation in that archive in JEDI today with basically no effort.
Okay.
There's still some historical stuff we have to go through for satellites we haven't. There's always nuance with particular types. We still have to pay attention to those details, but 90% of the work's already done.
Sounds great.
Any other questions or comments? Yeah, Kevin, go ahead.
Yeah, I think this question is for Shugong or maybe Jing Chen. I don't remember which talk it was, but you showed the results from the self-cycled paths. And I think there was a statement on there that said results were similar to GSI. And I was just curious, how many data sets were being assimilated in those experiments, and maybe a broader question about how we're sort of tracking what needs to go into the HASS JEDI system. Do we have like a checklist of what's been implemented, kind of the progress that's been made, and what's remaining to be done, at least in terms of the forward operators?
Yeah, I think I want to clarify the question first. You meant about self-cycled HASS system that myself introduced during my talk, or you're talking about a self-cycled HASS system that Cong Han was talking about in his coupled error covariance?
I think it was your talk. I think there was a statement on the slide that said the results were similar to the GSI.
Mm-hmm. Yeah, so right now we just use GSI as like a reference when we actually transition everything to JEDI, and we think because we have a lot of experience with GSI and observations, and we currently have tested it with limited observations like job sounds and radio sound. So we already spot differences between the two. I think as also Jing alluded, there are differences between the two in terms of QC, in terms of interpolation and detail about the minimization error and localization, etc. So, longer term, we want to actually leverage no efforts for the observation component and then bring them all into JEDI, and then use that as a reference before we develop, more research using more novel observations like cloud irradiances and, UAS observations, etc. I hope that addressed your question.
Yeah, it does. Thank you.
Yeah.
I assumed that was the case, but just wanted to confirm.
Mm-hmm.
And from our side, I mean, Zach's in here and Jing and Chu, we have a draft transition plan for which we have these specific things mapped out along with the things we have to go through and check the boxes in terms of observation types and capabilities and requirements for an initial operational capability for HAF. So it's there. I would like to see better coordination now with Cadre, for example. So we have disparate workflows in development that we have to figure out how to make sure that we stay efficient and the work happening in the research community is relevant to and can be connected to what we're doing within our workflow. We have the same issue in the global side. We have a global workflow that we use to transition innovation to operations that the community probably isn't using more broadly. So we just have to make sure that we find ways to keep these things connected in so much as we can.
Maybe a quick follow-up is how much, I don't know how about a term, chasing the observing system will be done, where we want to keep, bringing in more novel observations. I guess in the requirements, there has to be a cutoff at some point. I don't know if that's captured in the planning or not, but, you're going to have all these new novel data sets thrown at you, and the expectation is that they'll be assimilated in HAFS v2, given the current timeline, perhaps. And the risk of having to, stretch that to the right to accommodate these things. So maybe it's more of a comment just to be, the expectation that may be some pressure there.
So I actually don't know the details of what's in the plan. But I would challenge my team and the HAFS developers more broadly to focus on the things that are unique to and added value to the hurricane-specific problem. There's no reason to reinvent the wheel in terms of the stuff we're doing in the global and the satellite stuff. That work is already going to be done and largely transferable. But focusing on the stuff that's really going to matter for the hurricane problem needs to be the focus. And we've already started doing that with the UFO work that's happening in HAFS now is very specific to the stuff that HAFS is really going to need, and maybe the other applications don't need. We have a similar thing happening with RFS, right? So radar data is going to be critical for RFS. There's a lot of work happening in JEDI UFO for RFS within the RFS team. So we're trying to, the things for which we have separation of concerns, we're trying to focus on those things that are unique to those applications. Other questions or comments? Yeah, Frank. Oh, Aaron's coming. Frank.
Yeah, so I had a question for Jing. You were mentioning the timing issue for the cycle. Is that something that the model developers should be looking with you? For example, Bill, talking to you about so that we can speed up?
Okay, for that specific issue, that's related to JEDI analysis. So when we run the JEDI, and we found out, so with more JEDI member add-in, it requires more memory. So we kind of increase our node. So like for to manage to let it add more memories into that. And somehow we found out that once we increase the more nodes, the memory requirements increase too, and the running time increases too. So that's something very strange because we never see that in the JSI. And we kind of talk this with our EMC JEDI team, and they think this may come from like two sources. One is from the IO part, one problem from the JEDI. It's like I'm not sure it's a scaling problem or something like that. So that's something we need to rely on the GSSDA expert to help us to tackle that problem.
Tom, perhaps you have a comment.
Yeah, so I would definitely like to follow up with you on this and see, especially how we can collect metrics of measures of memory use, wall clock time, scalability, and metrics that we can actually reproduce, so that we can actually see how these are general problems that are seen across different applications that that will hopefully be addressed by some of the work that is ongoing on optimization. So I would strongly encourage to follow up on measuring and reproducing, so that we can only improve what we can measure.
Yeah, thank you. And just for information, Xu has already opened an issue in the JEDI repository to mention about this. So maybe if anyone, is that just I think following that issue, it will be so kind of help us a lot. Great, and that's a great testament to these agile boards that are open. This is fantastic. Great.
Yeah, just to follow up on Frank's comment, for some of the moving nest stuff in FV3, we had to do we had some memory scaling issues as we went to the really large basin scale. So we had that sort of an issue. But yeah, it sounds like this is, a totally different code base. But yeah, sometimes you can have some structure in there that, scales poorly and you have to restructure that.
Xu, go ahead.
Yeah, I have a comment or question to Jing and also relate to your comment. First of all, Jing, a great job, and you made a lot of progress of developing the HAPS app, and so especially with the JEDI component. So I think Kadri definitely want to leverage the observation treatment you have put in place in HAPS app and put in the Kadri workflow. And in the meantime, the Kadri workflow has a self-cycled capability. If I know it may be a little bit longer term plan, but if you're interested in using the self-cycled HAPS component, to replace or supplement the JDAS ensemble, feel free to reach out for collaboration. And and I do have a question for you. If right now you're using 80-member JDAS ensemble to sample the HAPS error, and you showed a slide with the increments wind and temperature, I just wonder whether you have seen anything like showing consistency or inconsistency between the wind and temperature increments, and suggesting using self-cycled ensemble down the road.
So far, since the test results are very preliminary, we just got that like a week ago before this HFIP meeting, so we haven't dig deep into the thing. But I do realize that the wind field and temperature field, the increment are not like optimized. That's I think that's something we need to use. And also, yes, for sure, we would like to try the self-cycled ensemble to see how that gonna change the game here. Because so far, using JDAS ensemble members, we have to interpolate it onto HAPS grid and then do the and then launch the JDA analysis. So we just wonder if using several HAPS maybe still gonna be different. And also on the increment side, I actually keep noticing the temperature field increment is pretty small. I don't know why, and that's something also need to look into. And thanks.
Shiguang, was your question in the context of JEDI or in general?
I just want to use the opportunity based on what Jing showed in her slide to help us understand more to what extent the ensemble sampling from JDAS is going to be sampling the actual HAPS error. Yeah.
Well, okay, yeah, sure. So I mean, Xu, you did. So I don't want to step on you, but I think you should describe the experiment you ran.
Yeah. Actually, I'm going to mention this about tomorrow. Anyway, so kind of like repeatedly, we have seen this issue of using the JDAS covariance can create significant, degradation in analysis. Something we've seen, yesterday or this morning, there's kind of weird analysis in the HAPS A configuration that's mostly coming from the JDAS, using the JDAS ensemble. And I will show you tomorrow if we are using kind of like self-cycled HAPS ensemble, not self-cycled, just 6-hour forecast from the co-started HAPS ensemble when we relocated it, and it will produce a much more reasonable analysis as compared to using the current HAPS JDAS ensemble.
Yeah, I mean, I think that's a pretty big deal, right? So we don't have to, in itself, we don't have to cycle. We could just have a short-term ensemble forecast with relocation, right?
Yeah,
And this solves this terrible issue we've been dealing with.
Yeah.
The halves ensemble itself, the cycled ensemble, one of the issues we've had is over the basin scale, we've had issues. We've tried these experiments and the results, even though we take care of this inner core issue, we've had issues on the larger scale, right? And so, one potential solution to this might just be, at least for the short to medium term after we get JEDI in, is to have just a short term, spun up ensemble with our own, covariance in implementing the ensemble relocation to get this inner core problem right, but still, not get so far off what's on the large scale from the global, so that we don't have other problems.
Exactly.
Yes. Sure.
All right, thanks. We're at time. I know people are ready to go to happy hour and relax for the evening. So I think it's clear from this session that both JEDI and coupled DA we're making significant progress already. I'm really excited that as we start to mature the JEDI capabilities, it's going to open the door to all kinds of science and innovation. We have a lot of stuff we didn't talk about in terms of new solvers and background error and things like considering hourly updating, high frequency type stuff, things that are going to help with the TC problem. But we made a lot of progress on JEDI already, and it's going to set the stage for all the exciting stuff we want to do. I also want to say that the initial JEDI implementation in HAFS v3 does not have to be a replication of what we're already doing. We need to benchmark it, but we now are to the point where we should start thinking about the science and innovation we want to target as part of that initial implementation when we're ready to do that. So with that, please join me in thanking all the speakers from the session again. I won't be here for later this week, so I wanted to thank Will, Aaron, and Liz for everything you've done already for this week and what you do for the rest of the week. So thanks again.
Thank you, Bill. All right, thanks everybody. That concludes today. Tomorrow, note we start at 8:15 instead of 8:30, and we will be going until 5:45 instead of 5:30 because of some sessions we had to tweak. So thank you. If you need to get your parking ticket out, go see Jason in the maroon shirt in the back waving his hand.